else than the head count. Hey, well, good afternoon, everyone. Today we'll be doing section 3.2. This is on measure of dispersion. 3.2, it's on measure of dispersion. Dispersion meaning the spread of data. So we're really going to look at, we're going to come up with numerical values to determine is the data really spread out, or is the data all close together? Before we get into that, the last thing we did was we talked about measure of central tendency with mean and median, and I want to do an exercise with the median because right at the end I was talking about how if your data is skewed, so if you got skewed data, then for the middle, when you come out the center, it's appropriate to report the median, right? Now, if your data is, roughly symmetric or bell-shaped, something symmetric, bell-shaped, that bell-shaped design where it's like this, the graph went up and goes back down, then for the middle, for the center, it's good to report the mean, all right? So if you want to talk about the center, we'll report the mean. So it's important to know, but why? So I would just give you an exercise, some numbers of why the median is a better representation of the center when your data is skewed. And I mean, just the idea here, I've got the numbers, let's say 10, 12, 16, 20, and 1 million. So you get 10, 12, 16, 20, and a million. We're going to compute two things. We're going to compute the mean and the median. All right? Feel free to use your calculator too. I think for the median it's going to be real easy. What's the median of this group?
16.
It's the middle, right?
Mm-hmm.
And then remember, it's already been sorted. 10, 12, 16, 20, 1 million. I didn't put commas in the million because I didn't want you to get mixed up with these. The median's the 16, right? Sitting right there in the center. Well, what's the mean going to be? I'll let you calculate it. So for the mean, we have to do what? Add up all the values
Divide by 5.
and then divide by,
And 5.
yeah, the sample size 5. There's 5 of them. Divide by 5, right? So add them all up. And you can do it. Someone will come up with an answer. Remember, I like to get someone to double check that for me. And we'll come up with this. You get an idea that it's going to be fairly large, isn't it? There's one player in that group. We'll call them players. There's one player who's really influencing this value, isn't it?
Outlier.
That's what's going to happen. So what do you get for the mean? So I add them all up. This plus this plus this plus this plus this. Divide by 5, right? What do you get for the mean? What'd you get?
200,011.6.
200,000 and 11.6. And I got a head. She's like, "Yep, that's what I got." So, what the heck's going on here? What's a better representation of the center here? The median, right? What did this one crazy value? We'll refer to it as an outlier. It's way out there, an outlier. What did that one value do to the whole group? It big time influenced it, didn't it? Had a major influence on it, and that's what can happen. So when you get data that's, when it's skewed, I'll go back and draw some of that. I'll get my eraser. You have skewed data, we know what they look like in a bell shape. That's bell shape, but skewed, it might look like this, and you got a lot of values here. But when you get these numbers that are way out here, you get a few of them, and they're way far away, these gigantic numbers like what? Like a million, can have a major influence on what's going on here. And so when your data is skewed for the center, it's better to report the what? The median. All right? Secondly, would you write this down? The median is resistant to outliers. The median is resistant to outliers. So we'll do an exercise for that too. What do you mean by that? Well, you just saw it. That was one example. It resists those outliers, right? That 16 was sitting there right in the middle. Didn't let that gigantic milling affect it. Cool. Hey, just by the way, have anybody ever looked at like, you know, homes in a certain area? Let's say like Anne Arundel County, and they give like the median home price. Have you ever noticed that? Mm-hmm. They always report the median home price. They never report the mean. It's always the median home price. If you're wondering why, it's because the data's skewed. It's always skewed. All right, so here's my exercise. All right, everyone, I gave a quiz yesterday, and I entered all these grades into Microsoft Excel. This quiz was out of 10 points, okay? So here's all the grades. And I'm talking on the telephone while I'm entering these, right? It was out of 10 points, you know. 2 students aced the quiz. I'm just entering it, and I'm talking, and I'm entering it. So you can see I made a typo. Does everyone see it? Mm-hmm. This quiz was only out of 10 points, but accidentally on this one, I was thinking 100%. What did I type accidentally? 100. So I made an error. All right, so now I'm going to fix it. I noticed it. I'm like, whoa, that student's average is way up there. So I'm like, oh, let me fix this. I got to make that 10. So I'm going to make the fix. 3, 5, 6, 10, and then I fix it. 10. All right, now it's fixed. Here's my question. This is before, this is after. I'm going to list some things over here. What's some measurements we've come up with over the past few days? The mean, the mode, the median. We did range, right?
No.
Oh, we'll do range today. But I'll just stick with these then. Mean, mode, median. The question is, which one of these 3 does not change? Which one does not change?
Median.
Between
The median.
before and after. I mean, look at that huge typo I have there. I fixed it. But with the before and the after, which one just did not change? We look at, all right, if we do the mean, we got to add them all up, divide by 5, add all these up, divide by 5. Do you agree these would be different? Mm-hmm. All right, so it's not that one. How about the mode? Number occurs the most.
Yes, it does.
No mode here, but we got 2 modes. There it is, 10. So that changed. Who did not change?
Median.
Resistant to outliers. Resistant to outliers. I mean, it's just a small exercise, but it gives you that idea, that sense. It kind of helps. Kind of stays in the middle, right? Doesn't let those crazy big numbers affect it. Especially when you get like 3 or 4 outliers in a row. The median will hold on and keep it right in the center. Hey, so today we're going to measure dispersion, and the first word that I like to talk about is the word range. This is a very simple formula. The range. Put this in there, so the formula sheet, attach your test. You know, throughout the course, there'll be like 3 formulas that are not on that formula sheet. One of them is range. Well, it's a very simple formula. It's just your highest value minus your lowest value, which I'll write as max minus min. So to find the range, it's just your max value minus your min value, your maximum value minus your min value. I'll erase that, sorry. So can you find the range of these 2 data sets here?
Before or after?
Do them both. Okay. What's the range?
97 and 7.
Good, 100 minus 397? Max minus min. What's the range of this one? 7. So did the range change?
Yes.
Yeah, I can add it to the group. That's one of these that would, median's still the only one that does not change. Resistant to the outlier. Well, that was a simple math formula. The one I'll take up the most today is something called the standard deviation. So you and I are going to find the standard deviation. Okay. For example, we're going to do this by hand. We're going to know how this math formula works. And then afterward, we'll go to technology, of course. See how that does it. But we're going to find what's called the standard deviation. So we're going to compute the standard deviation. Now, before I start, we've talked about the word sample and population in this course, right? So you're like, all right, are we finding the sample standard deviation or a population standard deviation? For our first example, we'll find a sample standard deviation. That's what we are going to compute, a sample standard deviation. It'll be the standard deviation of a sample, right? Rather not a population like something in the millions. Cool. Well, what is standard deviation? Deviation means like distance away or deviation, the difference from data points. So would you write this down? Standard deviation measures how far on average each observation is from the mean. I'll say that a few times. I know you're writing it down or copying this. How far on average each data value is from the mean. That's roughly what it's measuring. What's the standard deviation? In the end, we're going to get a value. We'll get a number. Well, what is it? It's a measurement of how far, on average, each observation is from the mean. Now, do you want? What's a simpler way to say it? Okay, it's the average deviation from the mean. Will that work? Like it's like a measurement of the average deviation from the mean. That's what it is. And that's what's important to us. We want to know what are we finding when we do all this. And deviation, everyone, we're just going to do a subtraction. So, sample standard deviation, I say we start with a simple example. How about the numbers 1, 2, 3, 4, 5? All right, there's our sample. I even put some neat braces around it. That's our sample, the numbers 1, 2, 3, 4, and 5. And we're going to compute the sample standard deviation. The standard deviation of that sample. All right. So we're going to compute sample standard deviation. Okay. Well, again, I said this is the average deviation from the mean, right? This is going to be 3 steps. What do you think step 1 is? Let me repeat again. It's the average deviation from the what?
Mean. So
It's the average deviation from the what?
Mean.
What do you think step 1 is?
Calculate mean.
Absolutely. Absolutely. That's it. We go step 1. Well, if it's the average deviation from the mean, our step 1 is we have to calculate the mean. If everything's based off the mean to come up with this computation, we're going to find the mean first. All right, so we're going to find the mean. Now, is it mean of a population or a sample?
Sample.
Sample. So
X bar.
I'll put the word. You remember this symbol for this?
X bar.
We're starting to get used to these symbols now. It's an X with a bar over it. You know, it's the symbol for sample mean. I'll go way over here. What's the symbol for population mean? It's a
Mu.
It's a mu. It's the Greek letter mu. That's for a population. So I'll erase that, but just so you can start getting used to these symbols. X bar, you can call it X bar. We have to add up all these numbers and then divide by, how many numbers are there?
5.
5 of them. All right, so we're going to add them all up. 1 plus 2 plus 3 plus 4 plus 5. Divide by 5. See what you get.
15 over 5, 3.
So you add them all up, you get 15. There's 5 numbers, and you get a 3. Is that when you get 3?
Uh-huh.
Cool. I wanted to keep it simple for our first example. It's the way to do standard deviation the first time. All right, so that's sample mean, X bar. Step 2 is the big step. All right, I think I've got enough room here. This is the big step. This is where I'm going to do all those deviations I was talking about. A deviation is just a subtraction. But didn't I say I had to do each observation? So that's what I'm going to do. So I'm going to make a fraction bar. Make it pretty big. And I'm going to take each one of these values. There's the 1. And I'm going to subtract the mean. I think I'll color code. Every time I do the mean, I'm going to put it in yellow. So take 1 minus 3, put a parentheses, close it, put a plus. Put a 2 minus the 3. Plus. Almost done. There's a 3. I got to take 3, subtract the mean. We know what that number is. 2 more. 4 minus the 3. And lastly, 5 minus the 3. And we're going to have to add something to this in a second. Not going to be hard. We're going to add something to this. But this, we're getting a sense of what's going on here. We're summing all the deviations, right? So far. Question?
I have a question, but I figured it out.
Oh, okay, awesome. Now, Aaron, don't you think we divide by 5 here? When we do average, we divide by 5 numbers, right? When you compute the sample standard deviation, you always divide by the sample size minus 1. So you and I are going to divide by n minus 1. And I know you're sitting there going, what? What is that? Why are you doing that? I don't want you to get so concerned about it, or the theory behind it. It's because this right here, it's because of the bias involved when you have these small samples that we divide by this. There's a name for this too. By the way, what's 5 minus 1?
4.
We're going to divide by 4. That's what we're going to do in this math equation. We're going to divide by a 4. It's n minus 1. So I'll put a 4 here and just make a note that this was the sample size minus 1, 5 minus 1. There's a name for this 4 though. It's called the degrees of freedom. All right. It's called the degrees of freedom. And I'll fix the numerator too. There's something else we have to fix in the numerator to make this math equation perfect. All right. What do you mean by degrees of freedom? There are 4 degrees of freedom, but there are 5 values in the sample, true? So just a quick exercise to help you understand this concept of degrees of freedom. Everyone, let's say, if you walked in here, I had 6 donuts in a box. You know, I had the sprinkles, I had the chocolate cream, I had the jelly, and I put them in here, you know, about 12:15, I put it right here. I put a sign, you know, Professor Mester here. Anybody's hungry, take one. And the first student walks in the door, right? They're starving. They haven't eaten all day. They see this. They're going to grab one. Do they have freedom to choose? 6 donuts, right? They grab one. That was only 5 left. The next student walks in the door. Ooh, donuts, hungry. Do they have freedom to choose?
1 less.
All right. There's 5 left, but they have still some freedom. The next one enters, the next one enters, the next one enters. Now everyone's taking the donut. The 6th person walks in the door. There they go. Donut. They see the sign. They come up in the box. Inside the box, there's that one plain donut. It's already getting kind of hard and stuff, right? It's getting kind of stale, but there it is. And they're starving, so they're going to grab it. But did they have any freedom to choose?
No.
No, they were stuck with the what? That plain. They were the one that didn't have any freedom. So there were what? 6 donuts, but there were what? 5 degrees of freedom. Does that make sense? So that's what we mean by degrees of freedom here when I'm saying there's 4 degrees of freedom. All right, so I think we got this thing all worked out except for one thing. Look at the numerator. Something's not working properly. If we're trying to get an idea of how things are spread out, mathematically, something funny's going on. We're going to have to fix it. Y'all notice it?
It will be like 0.
Ah, see, I heard people saying you get some negative numbers popping up. 1 minus 3 is what?
Negative 2.
Negative 2. You get a negative 2, and over here you get a positive 2.
0.
And a 1 over here, but this is a...
1.
So this isn't going to work out mathematically because in the end we're just going to get like a 0. That's not really telling us about the spread of data, right? So in this math formula, this is standard. It's called the sample standard deviation. The standard deviation equation requires that you square all the deviations. So would you put squares on each deviation? See, that makes them all positive, right?
Why can't you take absolute value?
I know, you could actually. You know? It could be the art formula. So I'm just going to take the absolute value of all these. And we're going to have to offset that eventually.
I will.
But this is for the find the what? Sample, the word standard. Maybe ours would be the art deviation formula.
Okay.
Hey, let's see what we get here. I'll let you sum up all those numbers in the numerator, and we're going to divide it 4. I'm trying it mentally, everyone. I'm getting 10. So could you verify that? It's like a 4 plus 1 plus 0 plus 1 plus 4. 4 plus 1 plus 0 plus 1 plus 4. 10. And 10 over 4 is?
5/2.
5 over 2, I think I'll write it as a decimal.
2.5.
2.5. Now don't forget, there's 3 steps. See, the third step, we're just going to have to offset all those squares we're doing. But is everyone okay with this? There is a name for this number. And I want to make sure everyone knows what this name is. In step 2, it's not the sample standard deviation. There's a name for this. All that right there in step 2, this is called the sample variance. It's called the sample variance. And eventually I'll show you the symbol. I can't show it to you yet. I'll show it to you. That's the sample variance. Varies, you think about varies, things what? How far away, right? The sample variance. And if you wanted to define that, look, it's the summation of the squared deviations, right? Divided by the degrees of freedom. If you want to talk like a statistician, true? It's the summation of the squared deviations, that's a deviation, that's a deviation, that's a deviation, divided by the degrees of freedom. Yeah. So what do you get? You get what's called the sample variance. All right, step 3, final step. How do you get the sample standard a deviation? One quick step.
For the numerator, will you always square it?
Always. And it's part of the standard formula. You got it. Great question. And now for this last step, I have to offset all those squares I was doing. So you know what we do? We take the square root of the variance. You take the square root of the last number. Does everyone know where the square root button is on your calculator? So I got to take the square root of what?
2.5.
2.5. Now, this can go out to about 8 places on your decimal, after the decimal place. It can go out about 8, even more places on those calculators. I say let's just take this out to 2 decimal places, whatever we get. We've got 2 decimal places. Put a little squiggle for equal sign. What are you getting? 1.58. 1.58? So I'm curious, what did it do? 1.5 what? 1.5811, blah, 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 blah. We're going to say, all right, the sample standard deviation is 1.58. Now, I want to show you these symbols. This is for a sample, right? Thankfully, they came up with a nice letter for sample standard deviation. Sample starts with what letter? S.
Yes.
Standard starts with what letter?
S.
S? It's an S. So now, I can show you the symbol for sample variance, sample variance. It would just be that squared. So when the symbol for sample variance is just S squared. Just square an that. You square that, you come to here. Right? So S is equal to 1.58. Hey, TI-83, TI-84 calculators, when we find this on our calculator, it writes it like this. It puts a subscript of X off the S. It's like the standard deviation of all the X values. So I just want to let you know that's how it looks on your calculator. You'll see an S with an X as a subscript.
So X is always represented as standard.
You bet. And it's a lower, if you're curious, like in the textbook, and you look on the internet, it's lowercase s.
So it's always going to
Yep.
be sample standard.
It's always a sample standard deviation. So you go, all right, what's population standard deviation, right? We'll get that symbol in a second. Is everyone okay with this?
Mm-hmm.
All right. Hey, more important than the tedious calculations, seriously, is understanding what this basically is doing for us. What does this measurement mean? So you go, what is 1.6? Well, we said it's the average deviation from the mean, right? So let's go back and look. The mean was 3. How far away is that from a 3?
But 2,
How far away is that from a 3?
1.
How far away is that from a 3? It's right on it, 0. How far away is that from a 3? How far away is that from a 3? 2, 2, 3, 1, 2. I mean 2, 1, 0, 1, 2. All right, on average, we're saying these data, each observation is roughly about what? 1.6 away from the mean. Gives you a sense of what's going on in terms of spread of data. And the more spread out, this gets really, really what? Big. Data's all tight. Think of a class and how the students did on a test. You know, if the standard deviation is really small, they all scored close to each other. But they're all over the place. Be very big. All right. Hey,
So in a case of outlier, the standard deviation might be really high.
you bet. That can really take, it totally affects it. Just one of them, right?
Yeah.
Just one of them can really affect that. I love it. All right, so that's the sample standard deviation. I say we create what the math formula would look like. Because there's a formula and it's attached to your test. It'll be there for your test, the next test you take, even on the final. But you want to see what it looks like? I say we create it. All right. What's the formula for sample standard deviation? What would S be? And if you want to put a little subscript X, you can, because the calculator does it. Let's see. First thing, it looks like I have to add things up, right?
Mm-hmm.
And when are we adding things? So what's the symbol for adding things?
Sigma.
Yeah, remember that things? That's the capital sigma, Greek letter sigma. I had to sum each one of these x values, but there were different x's, so I'm going to put x sub I. And what did I subtract from each x?
Mean.
And what's the symbol for the sample mean?
X bar.
X bar. So I'm going to put x sub I minus x with a bar over it. I'll close the parenthesis, and don't I have to square these?
Yeah.
And then I'll put a big fraction, and then underneath I put not n, but n minus 1.
1.
And there's one more symbol I have to add to this. What do we do in step 3?
Square root.
So this thing looks like a monster, doesn't it? Look at that. Make sure I get that radical over the whole. So when you got the formula sheet the first day of class, some of you might have looked at that and went, good golly, what is going on in this math class? But once you do it, you go through it, you go, oh, that makes sense to me now. Summation of the square deviations divided by the degrees of freedom, then you take the square root of that, right? And if you just want the variance, you lift off that radical hat. It's just that squared. Cool? Awesome. Awesome. Now, hey, I want to show you these symbols for population. Okay? Can I erase all this? All right. I'll take this out of the way, get this out of the way. I just want to show you the symbols so we can stay organized before we lose sight of all these funny symbols popping up. I say we start with mean, and then we'll do standard deviation. All right. Symbols. Just a quick symbol review. Mean versus standard deviation. All right, if it's a sample, what's the symbol for sample mean? It's an X with a what?
Bar.
What's the symbol for population?
Mu.
It's that Greek letter mu. So you and I right now, you go, what is this? We're just getting organized. See what all these symbols are. Now we know this letter. What's this?
SX.
S. If you want to put a little X on the subscript, you can. It's an S. And now I'm going to show you this one. See when they call these populations, they call them parameters. And they use Greek letters. So you bet, this is going to be a Greek letter. The symbol for population, standard deviation, looks like that. You go, what's that in the Greek alphabet? That's lowercase sigma. That's sigma. That's not the uppercase, it's the lowercase. Just like we have capital A and little a, like lowercase, like, that's lowercase. But it's sigma. It's lowercase sigma. So you can just call it sigma. But it looks funny. When I was a student, everyone, I didn't know the Greek alphabet, I'll be honest. Years ago, I just called it O. It looked like an O. I'll go, your S, your U, your X with the bar on top, you know, the X hat. Made up names. Cool. Now, the formula for this, I want to show it to you. It's the same thing as this, except for one thing. It's the same thing. By the way, you don't subtract X bar. What do you subtract?
Mu.
Mu. But you don't do the n minus 1. You just divide by n. That's the only difference in a population standard deviation calculation. You don't divide by the degrees of freedom. You just divide by the what? The big N. You remember what big N meant? Size of the what?
Population.
Population, yeah. And a lot of times, isn't big N in the millions?
Yeah.
Right? A lot of times, big N is in the millions. So if you divide by 1,000,000 or 1,000,001, that's not going to be a big difference, is it? Yeah, that's what I mean. That's what you get a sense of. But when it's small, when there's small sample sizes, it does have that effect. Cool. Oh, I got away. I need to copy. Hey, if you're curious for your next test,
I won't have you calculate a population standard deviation, I'm gonna have you calculate a sample standard deviation, all right? I just want to point that out. You're curious, you're like, you're gonna make me do a population, you're gonna have to calculate a sample standard deviation. I'll give you a sample, and then I ask you to calculate the standard deviation of that sample if you're curious. Cool? All right. Super job.
Will we have to know the formula or just have?
No, these get attached,
Oh.
you know? But I'll be honest, I think you're probably not gonna look at that. I'm serious, watch. You're gonna be like, I'm just gonna calculate. What's important is, rather than the tedious calculations, you know there's a formula for it, you can do it, is understanding like, what does it mean?
Right.
That is really the thing. It's like, I wanna be statistically literate, I can look up the formula, but what does it really mean? It's like, on average, it's giving me how much, you know, the average deviation from the mean of each one of these observations. Awesome. Hey, before we play around with the calculator, let's do an exercise. I'll erase these formulas. I was just talking about statistical literacy. I want you to be statistically literate. And so I'm going to give you a little exercise here. We can come up with a solution. I gave some tests last week to the students down the road, right? As a midshipman. Well, this was the result of the test. All right. I put some symbols down. All my students, all midshipmen, that's what they got. This was last week on midshipmen. X bar was 52, it's out of 100. X bar is 52, S was 7. All right. Now, I handed back the tests. Student goes, hey, professor, can I ask you about number 2? I looked at number 2 and I'm like, you know, you're right. He was making an argument for number 2, you know, the wording used. I said, you know, you're right. So you know what I'm gonna do? Number 2 is worth 5 points. And I said, I don't care if you got it marked right or wrong, no matter what, this is what's gonna happen. Every student is gonna get 5 points added to their score. Okay? Every student took the test. Everyone's gonna get 5 points added to the score. You know? Susan's gonna get it, Joe's gonna get it, John's gonna get it, David, etc. Everyone's getting 5 additional points. All right? So 5 additional points are being added. To each grade. All right? You're going to help me come up with these 2 numbers. Now, if you know it, don't shout out. I want you to start thinking about this. All right. I know what you're thinking. Some people in the room right now are going, how many students are in the class? How many students are in the class? We don't need that. Because I said each student, right? Each grade, each one of the students' grade got 5 points added to it. So, remember what was going on before? I'm going to use my hands. Everyone, here's that 52. It's in the middle, right? There's that 52 in the middle. And on average, everyone's about what? 7 away from the mean. This is like the distribution of grades, right? There's the very lowest, the min, there's the highest, but on average they're about roughly what? 7 away from this what? 5. And everyone got a 5 added to it. When I do that, this whole thing's going to basically shift like this. So, what do you think the X bar is going to be?
57.
You nailed it. Everyone agree? Everyone got 5 points added. What's going to happen to the average? It's going to go up by what?
5.
5. 57. If Joe got it, Sue got it, David got 5 points, and what's going to happen to the average? That's going to go up by 5 points, right? Now, before you come up with this, I want you to watch my hands again. Okay? All right. Here's the grades before I added the 5 points. In the middle is a 52, right? Now I added the 5 points. Remember, standard deviation, we're thinking of the spread of data. Watch the spread between my hands. Shh. Now the grades are here. I want you to look at the difference, the distance between my left hand and my right hand. I'll do it again. It was over here. There they are. There's that 52 in the middle. Now everyone got 5 points added to the grade. Shh. What about the distance between my 2 hands?
Decreased.
Didn't change.
Oh,
What's going to happen to this standard deviation? It's going to stay 7. Now everyone's on average 7 away from the what? 57. Yeah, statistically literate. We get that. We understand that. Very good. There you go. You nailed it. Okay, the mean went up by 5, but the standard deviation stayed the same. Stayed 7. Cool.
Awesome. Hey, let's go to technology. Let's go to chemistry.
Absolutely. You can use this throughout the course to facilitate the tedious calculations. I'm going to hit this slide, okay? I'm going to put you to sleep. All right, the first thing is I need you to find the stat button. I'll hold it up like this, the stat button. It's up near the top in the middle, the stat. And I'm going to hit stat, and you get a menu like this. And I just want you to hit enter. See how it's on edit? Just hit enter. And you get something like this. Now, a lot of yours might be blank. That means no data in there. You see how I got data in here? Who's got blank data? It means all you, awesome. So you get the enter stuff in right away. I got stuff in the way. I got to clear this out. So what I do is, I'm going to use the up arrow. And I'm going to up arrow to that L1 right there, right? I'm going to hit the button clear. If you can, on your paper, would you write down clear? It's a good button. I'm going to hit clear. Where's clear? It's right near the lower arrow. Want to see clear? So I'm going to hit clear, and here I go. Watch me do it. Clear. Now, did anything happen? No, because now I have to hit enter. So I want you to know that. So you go, why did anything happen? I have to hit enter, and boom, boom. Cool? But warning, if you go up there and you accidentally hit the word, I should whisper it, delete. If you accidentally hit delete, guess what's going to happen? You're going to remove L1 from your calculator. Okay? I would bet, you know, $100 it'll happen to at least one student in the class. It always happens. I think it's a design flaw. They shouldn't allow it to happen so easily. If it happens, would you just see me? I can help you get it back. It's not hard. So if you're like, I lost my L1, let me know. All right? I know on a test I won't be able to help you. You go, what will you do? Just use L2. Just use L2. Just don't delete all of them. Right? But yeah, use clear, right? So if I wanted to clear this out, what do? I hit clear, and then what do I hit? Enter. There you go. So we're going to go in here. What were the numbers from our data set before? 1, 2, 3, 4, and what? 5? All right, hit add. Hit 2. Hit 3. Hit 4. By the way, to make it move, I'm hitting enter. Hit 5. Type them all in. All of those are L1. You bet. You can use L1 over and over in this course. And when we need 2 columns, we'll use L1 and L2. All right? All right, everyone done? Hey, unfortunately, there's no like escape button here. Like to leave this, almost like think of this like a web page. There's nothing here to leave it. So what I always say is quit. So you know where quit is? You're going to hit that second mode. So I'm just going to quit out of the screen. So I'm just going to hit second mode. Mode is right next to the second. So to get that quit, I have to hit this second, and then mode, it goes up. I just want to say, all right, it's all in there, right? Now I want this tool right here to do some things for me. I want to get the sample mean, and I want to get the sample standard deviation, right? Okay. So I'll go back in, back to stat. Now I'm not going to hit enter this time, am I? Because I'd go in a circle, wouldn't I? I go back to stat, and when I want to arrow to the right to that calc, so use the right arrow and go to the calc menu. Calculate. And it's number 1 on the list. So if I want this, there it is. It's called one variable stats. I'm just going to hit enter. Nothing happened because I have to hit enter again. So remember that. When it does that, I hit enter and you get this. I just hit enter again. And everyone, you can use your down arrow. This list goes really far. Goes down a ways. So you can use that down arrow if you want to look at everything. Look at that. How far it goes down? What's those Q1s and Q3s? That's coming up after test 1. We'll get to that later. But what I love is, does it give us the median? Mm-hmm. Awesome. Does it give us the sample mean? Mm-hmm. Everyone see X bar? And does it give us the sample standard deviation? Mm-hmm. Awesome. Hey, do you notice? There it is, 1.5. Is that what we got? Mm-hmm. 1.5? There it is. Do you notice it does a population standard deviation formula? Yeah. That was where you just divided by, that would have divided by 5. Obvious. But hey, remember when I say in your task, which one am I asking you to find? Sample. Just so you're not stressing about that. I'm going to have you find the sample standard deviation. I'm not going to give you like a million numbers and go get the standard deviation. Right? Give you a group. It might be like 20, 25 numbers.
Mine's not coming up on mine.
What's that?
It's not coming up on mine.
It's not coming up on yours? Let me see it real quick. I'll fix it. So you come in here and you go in here and let's see what you got. So you're down here, you get list one, and then you're going to just go down to calculate. There you go. You're welcome. Hey, so that was a good question she just asked. Who has a newer model? And what happens on your newer model? When you went that screen, you had to go down arrow to a button called calculate. So you figured out, everybody else have the newer models? It might be at home or something, I just want to let you know that. It's not exactly like you saw. When you went to that screen, I hit enter, it would have another screen that goes, I think it said list L1, and it said calculate, you would hit calculate. And I'll do it for you. Cool. Hey, can you use this on the test? Yes, I encourage it actually. Because more important than the tedious calculations is what? You know, you can do it by hand, but everyone, what if I had you do 40 numbers? And the numbers were like 6.825 and 22.92. Could you imagine how long that would take, that process? I better give you an hour for one problem, do you agree? You follow me? So that's what's more important than the tedious calculations is the, understanding of what it means and what it means. Cool? All right. So you can use that. I encourage you to, especially when you get a bunch of numbers. But see, you understand the concept of standard deviation. You're statistically literate. So without that tool, now if you know this answer real quickly, would you hold off from letting everyone know? Give everyone a chance to think about this. Standard deviation. All right. You're not allowed to calculate on this one. I want you to find the standard deviation of that set of group, of the set of data. Now don't shout it out, but who already knows the answer? All right. Take some time to think about it. I want you to find a standard deviation of that group. Standard deviation, like what does that measure? It measures on average how far each observation is from the what? The mean, right? Okay. Well, I have an 8 and an 8 and an 8 and an 8 and an 8, right? But you and I, we're going to be statistically literate. We're measuring the sample standard deviation of this. Okay, well, 8, 8, 8, 8, 8. I'll find the mean. What's the mean?
8.
The mean is 8. Is that right?
Mm-hmm.
Okay. And now I got to figure out how far away each one of these values is from a what? An 8. Who thinks they have an idea of this number without even writing stuff down as you're thinking about this? Because I'm going to have to take that, subtract that, hit that, subtract that. Do you have your hand up? Oh, what's your name? I'm sorry.
Krista.
Oh, Chris, what do you get?
It's 0.
0. That's the standard deviation. That's the sample standard deviation. 0. 0 deviation, right? Everyone agree?
Mm-hmm.
How far away from me? 0. They're all right on the mean. Does that make sense? There you go. See, that's what I mean. That's more important than like, just crunching through all the math numbers. We're like, you get 0. We're all around the same. Hey, last thing we do, you're going to like this, is we're going to talk about the empirical rule. It's the last thing in section 3.2. It's called the empirical rule. All right, and this deals with bell-shaped distributions. It deals with bell-shaped distributions. All right. Can I erase the range formula? That's easy, right? Max minus min. Well, the empirical rule deals with bell-shaped distributions. What is the empirical rule? It's 3 numbers. Here they are. 68, 95, and 99.7. And they're percentages. So I should put percentage symbols next to these 3 numbers. 68%, 95%, and 99.7%. 68%, 95%, 99.7%.
Is that the universal?
What's that?
These numbers are the universal?
Oh yeah, I'm going to show you what these numbers exactly mean.
Okay.
But it deals with something in terms of the amount of data inside the distribution,
Okay.
which will be bell-shaped. But only, does this deal with skewed data?
No.
Good, only bell-shaped distributions. So I'm gonna have to come up with something in real life that is a distribution that's bell-shaped. I think I'm gonna do the height of men, all right? Because everyone, it is bell-shaped. But I think I'll just do ages like 20 to 30 because what happens to the height of a man? He gets like age 65, 75, 85. What happens to his height?
They decrease.
Starts shrinking. Yeah. So I'm gonna just say, all right, age of men 20 to 30 years old. Sound good? All right. Well, the mean. I'm doing a population. I'm talking about all men. It's roughly about 70 inches. You really? Yeah. The book has it at 69.6, but I'm gonna use 70 inches. For our first example, just a neat integer. The standard deviation is 3. And why am I using these Greek letters? Because I'm talking about all men, right? Now, and I know I just introduced these symbols to you, so we should probably next to them write the words. This is the what? The population mean. And this symbol is the population, oh, we can abbreviate. How about SD? Does that work? Mm-hmm. We'll just put SD. That's the population standard deviation. And you and I are going to draw a bell curve to represent this. We're going to draw a picture. And then I'll talk about the 68, the 95, and the 99.7. Okay? But now when you see that, the mean height of man, 70 inches. I mean, that's 5 feet, 10 inches tall. But the standard deviation, on average, each man is about how far from that mean? 3 inches. Okay? All right, so first thing is I'm going to need you to draw a bell. Yeah, it doesn't have to be perfect. Mine isn't. Draw a bell. And put a tick mark right in the middle. Right there. And we're going to do 3 tick marks to the right, right? 1, 2, and make this third tick mark fall about where this thing's starting to flatten out. You'll see a ton of these images in the book or in my Canvas course in the notes. And then on this side of this middle tick, I need you to put 3 tick marks. Spread them out. 1, 2, and then that third one, everyone, just make sure it's, you know, roughly right whereabouts. Doesn't have to be perfect. So here's the distribution of men. I'm going to label these tick marks. Sound good? Let's start with that one. I bet you someone knows what number goes there. Look at those 2 numbers. Who's smack dab in the middle?
70.
70! Everyone agree? Mm-hmm. The mean, the middle, 70. Now, on average, everything was 3 standard deviations of the mean. So I'm going to have to go one of those 3 higher. Mm-hmm. So I'm thinking I'm going to add one of these guys. That might be confusing to you. I'm going to add one of those guys. But that was equal to a what?
3.
So 70 plus 3, what's that number?
73.
All right. I got to add it again. I got to add another 3. What would this be? Remember, I don't want to confuse anybody. You go, what did I just do? I added 2 of those, didn't I? So the language is I added 2 standard deviations. Oh, this is 2 standard deviations above the mean. What will this be? 79? Mm-hmm. So when you understand, I just kept adding 3. Hey, if you like to use the math terminology, what did I do to get to here? From the mean, I added what? 1 to get that. To get this, I did what? I added 2 of those things. What's that? Oh, the standard deviation. And for this, what I do, I took the mean and I added what? 3 of these funny things. You don't have to write that down, but you might see this in a book and go, what does that mean? And you go, oh, that's easy, I get it. This is the height of a man who's 79 inches tall. And that's 6 feet 7 inches tall. That's tall. Anybody know somebody that tall? I have a friend. Look at him. People know people this tall. Well, that man, I'm talking about one individual. He is 3 standard deviations above the mean. That's how we talk, right? Or does anybody know someone in here who is 6 feet 4 inches tall? All right, that individual, he's 2 standard deviations above the mean, right? Cool. Hey, let's go on this side. Guess what I have to do?
Subtract.
Subtract. What's this? 67. What's this? And this?
61.
All right. So I'll get this jargon out of the way. We'll keep that picture. We're going to highlight it. There it is. There's the distribution of men. Now, do you agree there are people in this world who are actually taller than us? So I know I ended my curve here, but it really goes on infinitely, doesn't it? Because there could be a man who's 8 feet 6 inches tall, right? Or there'd be a man who's like 3 feet tall. Absolutely. So if you want, you can put a slight arrow there if you want. Just indicate this really keeps going. But there's not much out there. There's not many people beyond that. True? And there's not many people beyond this. That's 5 feet 1 inch. There's not many people, you know, shorter than 5 feet 1 inches. All right, now, what are these numbers? Go in the picture. Go 1 tick mark to the left of the middle and 1 tick mark to the right. So that means 1 standard deviation to the left, and then you go 1 standard deviation to the right. Go up and hit that bell. And maybe I'll improve my little bell there so it looks a little better. I want to get up there and then come right there. I'll like get it go up there and I'll like come down and then, yeah, that looks better. That looks a little better. Let it hump over there a little bit more. Okay. There you go. Inside here, when I'm going to shade, I need you to shade, and put the number 68%. And I'll say it in words. 68% of data in a bell-shaped distribution is within 1 standard deviation of the mean. Say again, 68% of data in any bell-shaped distribution, all right, is approximately 1 standard deviation from the mean. Or if you want to say approximately 68%. That's how we talk in statistics. Approximately 68% of data is 1 standard deviation from the mean. Within. So 1 below or 1 higher, right? 1 tick mark this way, 1 tick mark that way. Cool? So that's why that number was given as the empirical rule, the very first number. Now, does this only deal with height of men? No, this goes for any type of what? Bell-shaped distribution. It could be height of women. It could be weight of babies, right? When they're born. Well, anybody know what's the average weight of a baby when they're born?
7 pounds.
See, they know. They know. This is like it's roughly around 7 pounds. They know this. Okay? It could be IQ scores. Maybe it's SAT scores. But there's a lot of these distributions that are roughly bell-shaped. Okay, and we can deal with this. And we know that approximately 68% of data in any bell-shaped distribution will be 1 standard deviation from the mean. Now, I used to erase this and get this number going, but I always worry when I do that, I'd grade students' tests and I'd be like, why are they messing this up? And I realized it. I go, I need to draw 2 of these separately. So I'm going to draw another one, okay? Identical, but I'm not going to shade in the 68%. But if you don't mind, I'm just going to go, ooh, come back up, go back down. You know, it doesn't have to be perfect, right? Tick mark in the middle, 73, 76, 79, 67, 64, 61. It does not have to be perfect. Look how sloppy that bell is. That's okay. There's my bell. I'm going to label it again. This was 70, this was 73, 76, 79, 67, 64, 61. And you recall 68% of data is within 1 standard deviation of the mean. Guess what this is dealing with? It's from the middle. It's from the mean. This time I'm going to go out 2 tick marks to the left, 2 tick marks to the right. From the middle, I'm going to shade. I'm going to shade. I'm shading a lot here. Man, this is almost the entire bell, isn't it? So guess what percent of data, approximately, is within 2 standard deviations of the mean? 95%. 95% of data, approximately 95% of data in any bell-shaped distribution is within 2 standard deviations of the mean. And that was 1 standard deviation above the mean. That was 2 standard deviations above the mean. This was 1 standard deviation below the mean. That was 2 standard deviations below the mean. But 95% of data is within 2 standard deviations of the mean. So far, so good? I don't think I have to draw a 3rd picture, but I bet you know what happens here.
99%.
I mean, that's almost 100%, right? Almost. Guess how far out I'd shade?
The whole.
I know you know it, you
almost.
got the 3, right? Now, why isn't that 100 then? We know, there's a few individuals in this world who are what? Out here.
Exception. Yeah,
Does
outlier.
anybody know Shaq? Basketball?
Yeah.
Shaq O'Neal, yep. Shaquille O'Neal, I mean, he's like, I know he's over 7 feet tall. Or right around there, so he'd be over here somewhere. So that's what we mean. So that's why it's not 100%, but you go 3 standard deviations from the mean, 99.7%. All right, that's the hardest part. On the last problem of your test, I'm gonna have you draw one of these. But, and when I might do like IQ scores or SAT scores, but I have to give you these 2 numbers, don't I? Right? If you're like, do I have to know those symbols? No, actually, I'll say the population mean. I'll give it to you. I'll give you these standard deviation. I'll use those words. But once I give you those, you can build your picture, right? Start with the what? The mean, and then you can build 3 this way, 3 that way, right? Once you do that, I think you're going to be fine. So here come some questions for you. Right? Letter A. Blank percent. 20. Because you're like, what kind of questions are you going to ask at the end of that? And I'll tell you which problem this is like in the book. Is between 67 and 73, question mark. You'll come up with this. Oh, go ahead.
Is it always gonna be like 3 tick marks?
Always.
Okay.
Right? We don't have to go 400, and those tick marks, they're called standard deviations, right? But we don't have to go out 4 or 5. If you went out 4 or 5, we could. There's not much out there, is there?
Right.
That's what we're saying. We're like, we'll go up 3 and we'll get to this. Every time, let that bell curve kind of flatten out right there. You know, you might even start flattening it out a little bit beforehand. Book does a lot better job with these nice bells. You'll look at those. That's the first question. I think you'll have no problem doing that because you know the empirical rule. How about this one? Less than 67. I can put inches. So when you hear the symbol for inches, it's a little tick tick. So it's less than 67 or greater than 73. I'll put a question mark. And when I'm using the words less than and greater than, if you're thinking of height of man, you could say what? If you want to change that to taller than or shorter than, please feel free to do that. Because I am talking about the height of men, true? In this problem, I'm talking about height of men, age 20 to 30. So I'm saying less than, greater than, I'm talking about their height. So if you want to go shorter than, taller than, that's absolutely right. I'm going to fill these in. And I got one more. I'll do his last name. See, once you build these pictures, or you might just make one picture, we can answer these questions. All right, what percent is between 67 inches and 73 inches? What percent is between 67 is less than 67 or greater than 73? And what percent is less than 64 inches? So, for the first one, we did all this hard work, right? We know these numbers. We were given this. We drew a decent picture, right? The bill didn't have to be perfect. And what are we coming up with that answer?
68.
68. And if I just, like, even on a test, if I just have a blank, we just make sure, just don't write that number. You always got to put the what with it?
Percentage.
Percentage, right? Unless you want to write 0.68. Make sure to put the percentage there, too. So I'll pretend like these weren't there. Symbol there. All right, this one's a little harder because this number is not showing up over here. What percent is, where's less than the 67? Over there, right?
Yeah.
Uh-oh. But we're going to get it. And that says, we're greater than, uh-oh, that's over here. But she has no idea how to do this. What would you do? She starts with 100%. I love it. So brilliant. She goes, all right, we're going to get this answer. She knows that all this, all the men, it's got to be 100% of men, true?
Mm-hmm.
We're doing 100% of the men, so we're going to start with 100%. She's going to subtract this. Now, some of you do this mentally, which is awesome. You just do this in your head, but I'm going to write it down. I'm going to take 100%. I am going to subtract
68% to see what's left over in these two spaces here, in these two gaps. So what's in these two gaps? 32%. So does that mean there's 32% here and 32% here? No, you know what to do. Cut it in half, right? Or divide by 2. What's 32% divided by 2?
16.
So let's go back to our picture. We didn't have to memorize that because we were able to do that quite quickly. True? We didn't have to memorize these numbers, but now I can go insert it. What's over here?
16.
16%. How much is over here? You want to double check? Add them all up. Does it add up to 100? Sure does. Now for this answer, this word or, welcome to statistics. And or we always talk about the summation. So they want you to actually add these two groups together. So what percent is less than 67 inches of this man, or greater than or taller than 73 inches? What's 16% plus 16%? 32%. See, I just can't stump you anymore. I will not be able to stump you. That last problem on the test will not be able to stump you. You'll be able to get it. All right, let's try this one, but which picture is going to be more helpful? This one. Because what number do they have there? 64, everyone were like, there's no bar, we didn't make our little bar there. So let's use this image to get this solution. So forget the 68, forget the 16, block it out, true? We're going to use the what? 95. But this one's tough because I'm asking about a gap. I'm asking about that gap over there. You know what's amazing though? I'm watching you. There's some people in this class just in their head going like this. And they're getting the answer in their head. And that's so cool. I mean, it's great. But I'm going to do all the math here. Everything again has to add up to what?
100.
100%. I'm going to do like you said. I'm going to subtract 95.
5.
That leaves me with
5.
5%. But there's two open tails here. So I'm going to divide it by 2. I'll take a 5 divided 2 on my calculator. Can I get 2.5, right? So what percent is in each one of these tails? There's a, I'm going to write it really small. You might not be able to see it in the back, so I'm going to put an arrow here and go. There's 2.5% of men in there. It goes on forever that way. And there's 2.5% of men in there. So what's the answer? 2.5%. Right? I don't think I can stump you. I'll try though, and I'll do a letter D, see if I can stump you. Ready? Blank. By the way, we always use this word roughly in this world. Because are you saying, Matt, when I state this, are you being exact? Roughly. Blank percent roughly of men. We'll put roughly before this. Roughly, blank percent of men are taller than. Can you fill in the blank? Blank percent of men are taller than 64 inches. Or you can think of this word greater than. So we go here. So you're talking about this and all that. What am I going to have to do then? Anybody know? It's
So-
more than 95, isn't it?
Yeah, so
It's the
97.
95% plus the what?
2.5, 97 and a half.
What's 95 plus 2.5?
97.
97.5. That's pretty high, isn't it? So everyone, we're leaving class day going, my gosh. And you tell your friends, do you know, 95% of men are between 5 feet 4 inches and 6 feet 4 inches. My gosh. 2/3 of men are between 5 feet 7 and 6 feet 1 inch. Roughly. Yeah, that's true. 2/3 of men right in there, in that group. Bell-shaped, everyone's packed in the middle, right? We're all in the middle. Cool, and that's how in the test. If you're curious about the test, I'm thinking about for Thursday, like 13 problems. But some will have like a part A, part B. You go what I mean, like this, part A, part B, part C. If you don't want to memorize this number, I'm okay with that, because that's near 100, but will you make sure you know these two numbers? 68, 95, so you can build this. 13 problems. I'm thinking like 4 of those I'll probably do multiple choice like we did in class. About 13 overall problems. You can use your what? Yes, you can. So if you want to practice that one variable stats button, do it. If you lose your L1, let me know. I'll get it back for you. Have a great day. Good job.